Hello, this video will cover some information from Chapter 18 of the Holt Earth Science textbook. That might have been a PDF for you, which means that the PDF will just focus on light years, Doppler effect, and then some telescopes. So really what we're looking at here is just kind of space exploration and how we do that and how we measure those things when we're looking off into space. Of course, in order to do so, we have to use telescopes to look any further than our naked eye can see. So when we're measuring distance in terms of stars, we use something called a light year, which is found right here. So the light year is the distance, so it's a measure of distance that light travels in 1 year. So you measure how far light goes, traveling obviously at the speed of light, and how far that goes in 1 year, which happens to be 9.46 trillion kilometers. You don't need to know that for a test. It's just a little tidbit of information. Remember, trillion is 12 zeros, so that's a lot of kilometers. It's very, very, very far. But the amazing thing is when we're looking at stars, we can be looking at stars that are thousands of light years away, which means that even traveling at the speed of light, it would take you 1,000 years to get into that solar system that contains that star. So we're talking about crazy huge distances. So the Doppler effect was this discovery that, we're now over here, that radiation appears different colors, essentially, based on whether or not it's moving towards or away from you. Right? So if we're on Earth and we notice that there's this thing going on called redshift, where the galaxy, meaning the stars in that galaxy, and the radiation, meaning the light waves and UV rays and all that, that the star is giving off, if that appears a red color, it means that it's moving away from us. So what I want you to think about, this is a really big idea here and very important conclusion. If we notice, and this is what we have noticed, that pretty much every single galaxy, not our own galaxy, right, every other galaxy has a red shift to it, meaning it appears that red color, that means that they are all moving away from us, which of course means that the universe is getting bigger and bigger. Right, that's the first conclusion that can be drawn. Number one is, whoops, not conclusion, universe is expanding. But differently, we want to think about a second conclusion, which, and I've given you kind of a prompt here, if everything right now is moving away, let's rewind all of that, and let's think about where it gets us, where the rewind brings us to at the start of everything. So I'm going to leave this one blank here because I want you to think about that, and we're going to talk about it a little bit more in class. But if everything's expanding, think about what we can draw from that, what conclusion we can make from this first initial conclusion. Just a little email notice there. So the telescope section, moving on down, there's a lot of details in here, and I don't expect you to memorize all of these things. We're going to just kind of know generally the difference between refracting and reflecting. It's good to have these details, and then we can generalize from there. So a refracting telescope has an objective lens. A lens is something like what you have in glasses. If you wear glasses, you have a lens there. It captures the light, and it focuses that light to then be magnified by an eyepiece. So the eyepiece is actually just, like a magnifying glass. They can't be too big or the objective lens starts to sag. What I mean by that is if you have a lens that initially looks like this, and right out here is your light years and light years away, there's your star. If you get this lens too big, it starts to sag under its own weight. It starts to dip down in the middle, and essentially it starts to break. This is how we want it to look, a nice normal lens, even though it's a terrible drawing. This is what, number two, is what we don't want it to look like, because essentially that would be like your glasses starting to be pushed inwards and inwards. That's going to mess up the image. So refracting are very good in small telescopes. And the lenses can be relatively inexpensive to make when we're talking about something small. But if we're looking for something big, and remember, the bigger the telescope, the more light it collects. The more light it collects, the farther into space we can see. So we started using reflecting telescopes, which are big, huge mirrors that bounce the light to to another small mirror, and then to the eyepiece. The eyepiece is what you look through. Much the same on a microscope. So the mirrors can be bigger. And the polished edges don't absorb light, which means that you're not going to get some kind of weird diffraction. And what's also good about them is the mirrors reflect colors of light at the same focus length, meaning at your eye, whereas lenses can kind of diffract and mess up the colors a little bit. So at some point, we'll go back over the idea of wavelengths and light, which we'll talk about soon. We might do a short lab activity on that. When you want something that can look even further into space, you might combine mirrors. You might have multiple telescopes working together, multiple reflecting lenses, all bouncing the light together to provide an image. So we can combine these. So why might we find telescopes in the desert or mountaintops or in space? Well, because of the atmosphere, meaning the gases, atmosphere is just the mix of gases that surround Earth. So those gases reflect off lots of types of radiation. Also, the water vapor, which is part of those gases, right? That water vapor might bounce the light in different ways, and it might move it in a certain direction and bounce it off, which means that you then wouldn't be able to actually see the image coming through clearly. And of course, there's also light pollution. Light pollution is not smog, but light pollution is if, you're in the middle of the city, it's very hard to see the stars. If you go out to the desert, now there's no city lights, you can see the stars very easily. So you would go to the desert or the mountaintop to avoid light pollution. It might also be, especially in the mountaintop, a thinner atmosphere, less gases that might bounce off the incoming radiation. Space, though, is probably the best place to be. If you can get a telescope into space, you don't have to worry about the atmosphere, because there is no atmosphere. There's no radiation that's being blocked by the atmosphere. When we're thinking about carbon dioxide and oxygen and water, those are all just molecules. And if incoming radiation, meaning light waves, so visible light, or infrared, or UV, or X-ray, or gamma ray, all of those types of radiation get bounced by our atmosphere. So a lot of it doesn't even enter into our atmosphere and down to Earth. So space is the best place to have a telescope, but it's very expensive to do so. So when we're talking about radiation, what the word is that we're talking about here is electromagnetic radiation. What that means is just different wavelengths. You can have big, long radio wavelengths, or you can have very short wavelengths. And we'll talk about whether the big, long ones or the short ones are more or less dangerous. These are like radio waves. These might be like X-rays or gamma rays. I bet you can kind of come to a conclusion of which you think might be more dangerous based on your exposure to each one. You sit in a car and you listen to the radio all day long. Those are radio waves. Are we worried about that? No. But if you go into an X-ray machine, right, you go in to get your arm X-rayed, they put a big lead vest over you. So that should probably give you a hint about whether short wavelengths or long wavelengths are more dangerous. So a lot of these, like X-rays, UV rays, gamma rays, and infrared, IR stands for infrared, that's this word, heat, a lot of that gets bounced off by our atmosphere. The gases in our atmosphere essentially block that radiation. Now for us, for humans, that's really, really good, because the X-rays, UV rays, gamma rays would kill us. If all of the infrared, meaning heat, if all of that got through our atmosphere, our Earth would heat up very, 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 very quickly. And it would all of a sudden be like Mars, where it's 400 degrees during the day. That would not be very comfortable for us. So it's a good thing that our atmosphere blocks all of that radiation. But if we're trying to see out into the distant light years away, into distant space, we actually want to see that radiation. So the best way to do that is put them in space, right? This big piece here is talking about the Arecibo, which is a huge telescope, 305 meters across, 3 football fields, essentially, or the Very Large Array, which is a whole bunch of radio telescopes out in the desert that are combined together. So this is something like 20 or 30 telescopes combined in a field that's 30 kilometers, right? So all of those radio telescopes all of those radio telescopes work together and can therefore receive more radio waves coming in from space. Arecibo is a also very, very big 305 meter wide radio telescope, I believe. That is just a very big version. Obviously, this one, the Very Large Array, is even bigger, being 20 or 30 of them. So the whole point with this big is a bigger telescope means more radiation being caught by that telescope, right? Whatever type of radiation you were looking for. So with Arecibo and the Very Large Array, you're looking for radio waves. If you build a small telescope, a small reflecting or refracting telescope, and then you build a bigger one, you're going to be able to collect more of that type of radiation, which would be visible light. So the bigger the telescope, the more radiation you can collect, and therefore the farther into space you can see. Can see farther, right? Because if you're collecting more light, even that distant speck of light that is a very, very distant star, you'll be able to see that relatively clearly because of how high-powered your telescope is, meaning how much light it can collect. Same thing for a big radio telescope. If it's a very, very, very big one, even those faint radio waves from way, way out in distant space can be caught by that huge telescope. So in this case, bigger is better. So that was a 10-minute rundown, giving you lots of background information on this. Hopefully this is helpful. Please let me know if you've got any other questions. We will be following up more on radiation, so if you've still got some questions about that, hold tight. We'll go over it some more.